In this tutorial, we are going to talk about the relationship between rotational motion and the translational motion. So, rotational motion is circular motion, and translational motion is a linear motion. Now, we want to see the relationship which is going to be there. After that, we are going to solve this interesting question. So, we know that whenever we're talking about the linear motion, we're talking about an object moving in a straight path. And we have three main equations under a linear motion. The first equation is the final velocity is equal to the initial velocity plus the acceleration times time. The displacement is equal to the v initial times time plus half at squared. The third one is v final squared, v initial squared plus 2 acceleration times the displacement. So these formulas, they are for linear motion, which we call translational motion. Now, when an object is moving around the circle, this is what we call circular motion. So when an object is moving around the circle, what we have to understand is that the force that is pointing toward the center is what we call centripetal force. At the same time, the direction where the centripetal force is, that's where we expect to have the centripetal acceleration. So centripetal acceleration, like in Newton's laws of motion, we know that force is equal to mass times acceleration. But in a case of circular motion, we have what we call centripetal force. Centripetal force is the mass times centripetal acceleration. So centripetal acceleration is given by v squared divided by the r, which r is the radius in this case. V is the linear velocity, the velocity which we know from translational motion. Now, we can replace v squared over r with what we have here. So the centripetal force is going to be m v squared divided by the r. That's where this formula is coming from. Now, when an object is moving around the circle, we know that we're going to have the angular velocity. So we have to know the relationship which is there between the angular velocity and the linear velocity. Okay? So we are saying that as it is moving, we have the angular velocity. Okay? In translational motion, v is what we call the linear velocity. D is what we call the linear displacement. A is what we call the linear acceleration. Under rotational motion, which is circular motion, this is what we call the angular velocity. This is what we call the linear displacement. This is what we call the angular this is what we call the angular displacement. This is what we call the angular acceleration. So there is a relationship which you have to see between these two things. So we're not talking about the linear displacement, meaning we're talking about this. And the SI unit is in meters. The SI unit for linear velocity is meter per second. The SI unit for linear acceleration is meter per second squared. The SI unit for angular velocity is in rad per second. Sometimes in some books they're going to tell you that it is in revolution per second. The SI unit for angular displacement is just basically in rad. Then the angular acceleration is rad per second squared. As simple as that. Now, what we have to know from here is that the first relationship before we go to the formulas, what we have to know is if I want to find the linear displacement, I have the angular displacement, I can use this formula. The linear displacement is given by the angular displacement times r. The linear velocity is the angular velocity times the radius. The linear acceleration is given by the angular velocity acceleration times the radius. So you need to know these formulas. That is very, very, very important. That is the first relationship which you have to know. Next, let's build up from here. we want to see the relationship now which is going to be there. So these formulas, they are for uh, linear motion. Now we want to see the formulas for what? For rotational motion. So where there is v, I'm going to replace in rotational motion. So this is what we're going to say. This is linear motion. So here I'm going to have rotation. So where I have v, I'm going to say this is going to be the omega final is equal to omega initial plus alpha times t. T doesn't change. Next, where there is d, I'm going to put theta. This theta is in lad. So I'll have this times t plus half angular acceleration t squared. Next, I'll have omega squared, omega initial squared plus 2 angular acceleration times angular displacement. So now these three are the formulas which we need to know under rotational motion. Then these are the formula for linear motion, or you can say it is translational motion. Now, after reading the question, it is very important for us to come up with data. Data is going to help us to know which equation are we supposed to use. In this case, we have got our equation, we have got our question, but before we go to our question, let's talk more about the lad, which is the radian, and the revolution. What we have to understand is that if something is spinning from this point, if it comes from this point all the way to this point again, that is what we call one revolution. So in one revolution there is 360 degrees. At the same time there is 2 pi lad. Okay, so when you want to convert from revolution to lad, you are going to be using to say in 2 pi lad there is one revolution. Okay, that is very important. We need to know that. Now let's read our question. So the question is saying a belt runs on a wheel of radius 44 centimeters. During the time the wheel takes a course uniformly to rest from an initial speed of 1.6 revolution per second, the distance, which is 29.5 meters of the belt length, passes over the wheel. Find the deceleration of the wheel and the number of revolution it turned while stopping. So when you hear to say the number of revolution, they are asking about angular displacement. Okay, now your answer has to, you can leave your answer in revolution, but in most cases you have to leave the answer in radian, because the SI unit for this is radian. Now let's have our data. They're saying that we have the radius, which is 44 centimeters. We are going to say 44 divided by 100, which is going to be 0.44 meters. Next is saying that we have the initial velocity, but this speed, as we can see, it is in what? It is revolution per second, which is definitely the angular speed, but it is the initial 1.6 revolution per second. But we always need to convert this to rad per second. So before we go further, let's first convert this to rad per second. Using dimension analysis, I can say that 1.6 revolution in 1 second, I'm going to say in one revolution, how many rad do I have? Is 2 pi rad. So from here, I'm going to cancel the what? The revolution. So it's 1.6 times 2 pi. So this is going to give me my initial now to be 10.05, which is the same as 0.1 rad per second. Now I'm done with this. I also have the distance, which they are saying the d, which is 29.5 meters. That is the length. The question is, find the deceleration of the wheel and the number of revolution it turns while stopping. We don't have time. The only formula which can help us to find the acceleration without time, it is the third formula. But remember, we have the angular velocity, so it's going to be the omega final, the omega initial squared plus 2 angular accelerations times the theta. But we have got the distance here. We have to find the theta. The relationship which we have just come up with here is the linear displacement is equal to the angular displacement times the radius. Our goal is to find the theta. We are going to divide it by r, even here by r. Theta will be equal to d divided by the r. So let's see. D is 29.5. The radius is 0.44. So our theta is going to be 29.5 divided by 0.44. So now our theta is 67.045, or I can just say 0.5 to round it off. This is going to be in lad. That is my theta now. Now I have everything. Because it came to stop, I expect my final velocity, my final angular velocity, to be 0 because it came to stop. Okay? Now, let's plug in the values. We see what we're going to have. The final velocity is 0 squared. The initial is 10.18 squared plus 2. We want to find the angular acceleration. The displacement now is 7.05. So I'll shift this to the other side. I'm going to have negative 10.18 squared is going to be equal to 2 times 67.05. So this is going to give me 134.1 alpha. Now I can get rid of this. I no longer need this. Okay? Now I can divide both sides by 134.1, even here 134.1. So my alpha I expect to be negative because it was decelerating. Okay, so I'm going to have negative 10, so I'll say 10.18 squared, 10.18 I square it, then I divide it with 134.1. So I'm getting my answer to be 0.77. This is going to be rad per second squared. Okay, now if you want, this is going to be our acceleration now. This is my angular acceleration. The next question is, they want us to find the number of revolution. Okay, so there we go. I'll just put my angular acceleration to be here. Let's now see 0.77 rad per second squared. So now the question is, we have to find the revolution. Now, as you can see, the revolution, we are talking about the angular displacement. So the angular displacement, we have already found that it is 67.05 rad. Now they want it to be in revolution. What we have to do is just to convert this 67.05 from rad to revolution. Okay, so we're going to say 67.05 rad times in 2 pi rad. How many revolution do we have? We have 1 revolution. So in short, it's going to be 67.05 divided by 2 pi. So this is going to give me a 10.67. That is going to be now my revolution. So my revolution is 10.67, and in radian is 67.05. So that is it for this question.